Welcome back to the third and last part in this mini-series about TRIACs. And as promised, this video will be about practical considerations. This time my TRIAC is actually switching AC 24 volts RMS from this transformer through my electronic load. And the gate is driven by my power supply and a little series resistor and gets currently 2 milliamps. And while I'm able to switch on and off the whole thing, no problem, you might see that the lamps are flickering a little bit. So what is going on here? I'm basically using the circuit from the first part, only this is not a DC power supply anymore. It's an AC power supply, 24 volts RMS. And now my gate circuit is supplied by my DC power supply, and a little resistor for limiting the current through the gate. So why the flickering? Currently I have the positive binding post up here supplying the gate. So the gate is positive, always positive, in relation to the main terminal 1. And that means in a positive half wave from my AC supply, I'm operating in quadrant 1, gate positive, main terminal 2 positive, and in the negative half wave from the transformer, I'm actually in quadrant 4. Gate still positive, always positive, but now my main terminal 2 is negative in relation to main terminal 1. And you remember, quadrant 4 is a bit of a bad quadrant. It needs a whole lot more power, that is current, to the gate to switch on. That is, with just 2 milliamps through the gate, I'm only switching on for the positive half wave. And if I want to have the full sine wave going through my load, I have to supply more gate current. 7 milliamps seems to do the job. Let's have a look at the oscilloscope, what's exactly happening here. This is simply our AC from the transformer, 24 volts RMS. The pink line here near 0 is the voltage drop across our main terminal 2, which should be near 0 because we have the TRIAC switched on all the time. The yellow curve is the voltage drop across the gate, and you see when we are in the negative half wave, that voltage drop gets a little bit negative, and it's positive during the positive half of the sine wave. The straight line here is simply the voltage out of my power supply that goes through the resistor before the gate, and that little twiggly line here is actually the gate current. That is the difference between the voltage drop across the gate and what comes out of the power supply. Now, what happens if I decrease the current? We are currently at that 7 milliamps. And I'll go back. You can see it. In quadrant 4, so positive gate, negative terminal 2, the TRIAC is no longer switching on. And our gate current is constant. If I increase the gate current again, yeah, interesting thing happens until I reach, yeah, enough current to switch it fully on, 7 milliamps that was. And the gate current is actually fluctuating a little bit. Yeah, so it's not a constant 7 milliamps, what we've seen on the multimeter, but since the voltage drop across the gate here drops a little, yeah, or goes even negative, the current through the gate is increased. Now that's all not very nice, and maybe there's a way around that. Suppose we are really using some microcontroller, Arduino, PIC, whatever, to drive our gate. Nobody is forcing us to drive our gate with a positive current. TRIACs are a 4-quadrant device. We could, instead of connecting the ground, yeah, of our microcontroller to main terminal 1, we could simply connect the plus 5 volt rail or 3.3 volt rail of our MCU to main terminal 1 and then switch the TRIAC on by pulling our digital output to negative. And that, yeah, gates always negative, that would shift our operation from quadrant 1, quadrant 4 to quadrant 2 and quadrant 3. And there, yeah, we are still, yeah, have to provide more current to switch on the gate as compared to quadrant 1, but less, much less than we would have to supply in quadrant 4. And especially for that TRIAC, supplying 25 milliamps, worst case, at room temperature, yeah, you remember that one curve. If we running the TRIAC on low temperatures, we have to increase the current to the gate considerably. So, yeah, at 0 degrees by a factor of, yeah, worst case 1.5, at minus 25 degrees, at a factors of between 1.5 and 2. And, yeah, of course, our microcontroller unit would be struggling, yeah, times 2, providing 50 milliamps. There might be microcontrollers who can do that. Certainly no AT Mega and certainly no PIC. So if we simply reverse the polarity of our gate, yeah, we're now at minus 6.141 milliamps. We should be able to keep the thing fully switched on with a much lower current. Okay, so currently we need, yeah, let's say, be on the safe side, minus 4 milliamps instead of the positive 7 milliamps. And avoiding quadrant 4 operation has, of course, other benefits. If you remember from part 2, that limiting parameter here, the rate of rise of on-state current, it's a factor 5 lower for quadrant 4 than for all the other quadrants. So, yeah, doing it this way, yeah, have your microcontroller unit have the 5 volt or your positive supply array connected to main terminal 1 and switching the TRIAC on by pulling your digital output low. That's really the way to go. Our gate current is, of course, still fluctuating between the positive half wave and the negative half wave. The voltage drop across our gate is still going negative in the negative half wave, and it's going a little bit positive in the positive half wave. So the drop across the gate is really dominated by that higher AC voltage we are putting through terminal 2. So yeah, let's have a look what that is really in milliamps. So average gate current is about 4 milliamps, but it has an AC component, yeah, this little wiggle through the different phases, of 0.9 milliamps RMS. So yeah, let's say almost 1.5 milliamps peak. And you really have to take that into account when dimensioning this resistor here, especially when you are using a low voltage microcontroller, say not 5 volts but 3.3 volts or maybe even less, because at some point the fluctuating voltage drop and also polarity reversing voltage drop across your gate will dominate the output voltage on your digital output. This can really break or make your circuit or kill your microcontroller unit in extreme cases. But enough about driving the gate with, for example, a microcontroller. I have another problem here. My TRIAC is getting toasty, and I'm just driving 20 watts of light bulbs here. That transformer should be able to drive the full 100 watts I can switch here on, but that would certainly kill my TRIAC. So we need some cooling. And to calculate just how much cooling we need, we could go to this diagram, which shows us the voltage drop across the terminals in relation to the load current and for different temperatures. And here things get complicated because during a full sine wave, the voltage drop changes, of course. We could then multiply that by the current going through and do some integration and lots of complicated stuff to get the power dissipation at the junction. And then take the thermal resistance from the junction to the mounting base. Yeah, that's given 1.2 kelvins per watts. And then dimension a heatsink to use. Or we can use that diagram where most of the work has already been done for us. I mean, we have here the RMS current through our TRIAC, and we have here the power loss, which will be induced in our TRIAC by the current, and we have here the maximum mounting base temperature allowed. So let's say we want to drive our full 100 watts of halogen lights at 24 volts. That's a little over 4 amps. Yeah, be on the safe side. Let's see, we have 5 amps RMS current through the thing. Then we can go to the right curve, the one where we are on in each half waves for the full 180 degrees. Yeah, we switch it on full time. And that gives us a maximum mounting base temperature of 118 degrees. and a power dissipation inside the thing of 6 watts. Now we can forget about everything that's going on inside the TRIAC and just concentrate on the heatsink we are going to put on the back. We know that one side of the heatsink, where the mounting base is screwed on, we have a maximum temperature allowed of 118 degrees Celsius. And let's say ambient 40 degrees Celsius, yeah? That gives us a delta of 78 kelvins. So yeah, if you subtract Celsius from Celsius, you can directly go to Kelvin. Yeah, it's in that case, if you have a delta, it's Celsius and Kelvin is the same. So the thermal resistance we are searching for is the temperature divided by the power. So our delta of 78 Kelvin divided by the 6 watts we also got out of our diagram. And that means we will have to put on a heatsink with a thermal resistance of 13 kelvins per watt or less. So that's the maximum. Unfortunately, I only have here one with 21 kelvins per watt in free air. So back to the drawing board. So I looked at running the thing at 4 amps, so roughly 100 watts. Yeah, a little bit closer to our actual values. And got in the diagram a power dissipation of 4.7 watts and a maximum temperature of 119.5. The delta to 40 degrees Celsius is, yeah, well, it didn't work out. Then I scaled down to 3.33 amps, which would give us 80 watts at 24 volts. And then the whole thing yielded 3.6 watts power dissipation and a maximum mounting base temperature of 120.5. So delta of 80.5 K to 40 degrees ambient and 3.6 watts. And that yielded 22.4 Kelvin per watts maximum thermal resistance for the heatsink, and that thing has 21 watts. So yeah, with that heatsink I will be able to run it at, yeah, 80 watts. And yes, with just 2 light bulbs, that's 20 watts. It's, yeah, it's okay. But now it should survive, well, 80 watts. And yeah, it's a little bit bright. We let it run for a while. The heatsink, of course, is getting warm. But it seems to me it's not dying. So up to now we always experimented with some kind of this circuit here, where we have 2 galvanically isolated power supplies, one for the load circuit and one for the gate circuit. However, that's not the only way how to drive a TRIAC. At one point in the second part, I think I showed that diagram where we only have our AC source, and our AC source is driving, of course, through the main terminals our load. But at the same time, the AC source is also used to provide current to the gate. The example there was, using an optoisolator with a photo TRIAC inside it to control the TRIAC. Let's build something like that. And here it is. Instead of the optoisolator, I'm using a potentiometer to control the current through the gate. And my instrument is now measuring the current through my light bulb. And hopefully, yeah, that was a little jumpy, but still I can, well, I have some control. It's not that nice, but yeah, it's somehow working. Not quite as you wanted to, but yeah, nevertheless, let's have a look at the circuit. I have my transformer as AC source, and I'm switching through the TRIAC my light bulbs. At the same time, the AC source is supplying current to the gate of the TRIAC. And the current is limited by my potentiometer and a small fixed resistor, just to prevent shorts if I turn that down to 0. Now when the TRIAC is off, the whole AC voltage is dropped across it. Yeah, it doesn't exist. So the current through the gate is basically determined by the AC voltage and these resistors here. Yeah, we forget about the light bulbs for a moment because they are really low impedance. But as soon as the TRIAC turns on, I have basically no voltage drop here across the TRIAC, maybe a volt or so, and the bulk of the AC voltage is dropped across my load, the light bulbs. And that means I no longer have a voltage drop here across the resistors, yeah, maybe a volt or so, and the gate current is no longer supplied. So this kind of circuit works really in two phases. It's off, gate current is supplied, TRIAC is on, no longer any gate current is supplied, or very little. Let's have a look at the oscilloscope, how that works in reality. Now the pink line is the voltage drop across my TRIAC. At the moment the TRIAC is off, so the full sine wave is dropped across it. The blue line, that is currently as 0, is the voltage drop across my light bulbs. And yeah, the TRIAC is off, so no voltage drop there. Now I turn the potentiometer and something happened. So right there, here, you see that in the middle of the first half wave, my voltage drop across the TRIAC goes to 0, and I have a voltage drop across my light bulbs until we are at the 0 point and the TRIAC switches off again, so the second half wave is again completely dropped over the TRIAC. No current is going through my light bulb. If I turn a little bit further, I can switch on more and more of the half wave, okay? And now at some point, yeah, it's not quite stable, parts of the second half wave are always also switched through. Yeah, but it's not very nice, is it? It's not very nice, that phase control. And the question is, why? Let's go back to our doodle for a moment. So if I'm in the positive half wave, my main terminal 2 is positive, and of course my gate is positive relative to main terminal 1 both times, which is on the negative. If I'm in the negative half wave, my main terminal 2 is negative and my gate is negative, while main terminal 1 is positive. And I go back to the graphic from the first part. That means gate positive, main terminal 2 positive, gate negative, main terminal 2 negative. We are operating in quadrant 1 and quadrant 3 in this circuit. And if you remember, in quadrant 3 we need about twice as much gate trigger current to switch the thing on. So if I go to my awful doodle here, so in the middle that's the 0 line. That dotted line here is the gate trigger current required for quadrant 1, and that one here, about twice as far apart from the 0 line, is the gate trigger current for quadrant 4. So if my red, the voltage drop across my TRIAC rises, so rises my gate current until I reach the gate trigger current. And how fast that rises, it also follows a sine wave. That depends only on the values of these resistors. And as soon as I reach the trigger current, my resistor switches on and I have my voltage drop now across my load, which also means my trigger current, green, goes to 0. Now for the negative half wave, I have to wait a lot longer, of course, until I reach that twice as high trigger current. So my TRIAC will switch on later. Yeah, it's that simple. And also in that regard, using this circuit here, I of course will never be able to switch it on later than here 90 degrees when I'm at the maximum of my trigger current, or at 270 degrees when I'm here at the maximum of my trigger current. And that's the reason that with the same resistor value, I'm doing nothing to my pot here at the moment, I'm able to trigger in the positive half wave, but nothing happens in the negative half wave. And if I decrease the resistor value, I'm almost fully triggering the positive half wave, still is nothing happening here. And I basically, only very, very late in the game, I'm starting to triggering also here in the negative half wave. Independently which half wave is triggered, I always trigger at 90 degrees, the latest, because then the AC across the gate is the highest, and the current through the gate will be the highest. I'm not able with that circuit to trigger here beyond 90 degrees, between 19 and 180 degrees, respectively between 270 degrees and 360 degrees. It's simply not working. See? If I start triggering here in the negative, I start triggering here. I cannot trigger any later. Well, we would be able to alleviate the problem with triggering later in the phase of our AC, if we would just be able to shift the current through the gate a little to the right, you know, like I've shown here with the black line. And yeah, it's actually not hard to do that. All you need is a capacitor. Now you have here an RC circuit, and of course an RC circuit shifts your voltage, yeah, relative to the input AC. And yeah, well, I don't think I have a suitable capacitor for the job at hand. Let me cobble up something and let's have a look at the oscilloscope, how that turns out. So we are just looking at the positive half wave here, and that line is the voltage drop across my TRIAC, so the TRIAC is off. The blue line here at 0 is the voltage drop across my load, yeah, which is, if the TRIAC is off, 0. And this is my gate voltage without the capacitor. If I put in a capacitor, you see there is a phase shift, a slight phase shift in my gate voltage. And with the capacitor in, I'm now able to switch it on later, because you see the peak gate voltage is phase shifted to my load voltage across the main terminals. Yeah, and now I'm really here, yeah, well, not really at 0 degrees, but you get the principle. I needed a bigger capacitor to fully shift that by 90 degrees, but then I would be able to exert a full phase control. So that phase shifting actually works in principle. And now we are only one additional part away from the most basic, yeah, analog dimmer circuit, and that would be a DIAC, which we had to put here in between our gate and our RC network. A DIAC behaves much like a TRIAC, but it's triggered by the voltage difference between its terminals. And yeah, like for TRIAC, polarity doesn't matter. Unlike a TRIAC, it's very symmetric. So yeah, if it has a trigger voltage of say 60 volts with a typical value, then maybe in one direction you need 62 volts and in the other direction 85 volts to switch it on. And this behavior here, yeah, this will totally dominate any asymmetries you have here in the TRIAC regarding the required gate trigger current or the required gate trigger voltage. Yeah, this will hold off any trigger current until the voltage here is big enough to supply enough trigger current, whatever quadrant you are in, 1 or 3. So yeah, then the asymmetry will, yeah, the asymmetry problem will be solved. But I'm getting carried away. This is not a video about dimmer circuits. You will need some bells and whistles around that, like for example, somewhere inductivity to alleviate current spikes when you, yeah, switch on in the middle of a half wave, and maybe some capacitor to filter out these nasty spikes from your mains AC, etc., etc. But back to, yeah, datasheet stuff, I have one more point I want to make before closing this video. And this is about that minimum resistance you should have to your gate. In this circuit, in theory, yeah, if we look at it, I mean, we switch the TRIAC on as soon as we have enough gate trigger current. So yeah, all should be well. But what happens if my potentiometer is turned down to 0? And yeah, this is in some mains appliance, and we plug it in right in the moment where we are here at mains peak voltage. Yeah, then we would get a short pulse into the gate, a very high pulse. And we already talked about that when we were speaking about the limiting factors. That was the peak gate current. And I showed that back then in part 2 in this circuit. Okay. So when we really switch on at 90 degrees, we have, yeah, the problem that we have, the maximum voltage across here, yeah, between main terminal 2, between gate and main terminal 1, sorry. And yeah, we have to limit this peak current that will flow just for the moment the TRIAC needs to switch on. So we will get something like that, a spike, the red line, in the current. And the repetitive peak current, IGM, from the datasheet, that was that one here. And the peak voltage we have here. These are the two parameters which are used to calculate that resistor. And it's, simply, resistance is voltage over current. So we take our peak current, our peak voltage divided by the allowable repetitive peak current from the datasheet. In my case, I set 38 volts, 24 volts RMS plus 10% to be on the safe side, and times square root 2 makes 38 volts divided by the 2 amps from the datasheet, and that gave me 19 ohms. No, I don't have a 19 ohm resistor, so I played it safe and took a 22 ohm resistor. Usual values you find here for mains AC applications are a few hundred ohms. But don't, if you see in the internet some circuit like that and it says here 220 ohms, or sometimes it says 110 ohms. I mean, you never know, sometimes don't know for what mains voltage such a circuit was designed. Was it designed for 110 volts? Was it designed for 220, 230, 240? And you don't know, or you should know now, where to look into your datasheet to find out what current your TRIAC actually can take as repetitive peak gate current. Yeah, okay. That was the last point I wanted to make, I guess. And that was it. The third and last part of this mini-series about the dirty details in regards to TRIAC. That is mainly the stuff in the data sheets. In this video I just experimented a little, dabbled a little bit around and tried to make some references when to apply actually the stuff in the data sheets. Yeah, my battery of little capacitors for the phase shift. Yeah, it still wasn't enough. Anyway, bye.